Hi, this is Asha Nafisa, and today I'm presenting a video presentation on linear algebra and application on Math 1102. As it's a group presentation, me and my partner in this assignment, Junaid Sami, try to find out a problem along with its solution. Here is the short introduction of this topic. So, in the vast landscape of mathematical application, the idea of networking stands out for its broad utility in the modeling complex system. Networks, which are made up of nodes connected by edges, provide a structural representation that is useful in a variety of fields, including sociology, economics, technology, and engineering. This discusses the mathematical treatment of the network in two areas. So basically, these are traffic flow and electrical circuit. Utilizing graph theory and the linear algebra principle, we investigate how a network helps analyze and enhance network traffic system, improving flow and reducing traffic congestion, as well as how they are used to design and analyze electrical circuit, ensuring efficient and safely distributing. Through this exploration, we hope to demonstrate the power and versatility of mathematical networks in solving practical problems. So the problem I try to find out here is linear algebra problem, traffic flow formulation. So in this section, we look at the challenges of optimizing traffic flow in busy downtown area during rush hour, considering traffic lights and multiple entries and exit points. To simulate this scenario, we represent intersection as a nodes and street as a directed edges in a weighted graph, with ways representing average traffic loads. The system is expressed using a weighted adjacency matrix with the element Aij indicating the road capacity from intersection I to J, adjusted for a factor like traffic signals with that influence flow rates. The goal is to optimize overall traffic time formulated as an objective function. The second problem we work on linear algebra problem is electrical circuit problem. In this section, we will look at the analysis of a mixed electrical circuit that includes resistor, capacitor, and inductors. Our goal is to understand both the steady-state voltage and the circuit's dynamic transient behavior. To accomplish this, we define the circuit components as nodes and their connection as edges, resulting in a network. This network is further described using impedance matrix Z, where each element Zij signifies the impedance between nodes I and J. The applications of Kirchhoff's voltage law and current law helps us establish a comprehensive system of linear equation. This includes equation for direct currents steady-state analysis, which focuses on voltages and resistance, as well as alternating current AC transient analysis, counting for complex impedance of capacitor and inductors. So further on, we will discuss on these two problems and we'll try to find out the solution. Thank you.
Hello sir, this is Junaid Samit. So I'm gonna continue the problem she discussed earlier. So the first problem is to solve the traffic flow formulation problem. To solve this problem, we applied linear programming to optimize the traffic patterns in the downtown area. This method allows us to account for a variety of constants, including road capacity, traffic signals, and timing, that all of which are critical for managing in peak hour congestion. Linear programming identifies the optimal flow rates across the network by defining an objective function that minimizes overall time, and thus it lowers the bottlenecks and improves traffic management efficiency. This approach not only provides the solution but also reveals potential improvements to the infrastructure and the signal timing. The key points to this solution is the linear programming optimizations. To set up and solve the flow conversation equation is to use linear programming techniques. This includes defining an objective function that minimizes total travel time or maximizes through the while keeping the road capacities and traffic signals timings in check. Another point for this solution is the sensitivity analysis. To perform the sensitivity analysis, we check traffic patterns, road closures, or traffic signals so they may affect the overall flow. This can help identify the critical areas in our attention as well as potential infrastructure improvements. So the solution for the next problem, which is critical circuit problem, we also use linear for this one, the matrix equations. In this, complex matrix equations in electrical circuits are solved using techniques adapted for dealing with impedance matrices, which include resistors, capacitors, and indicators. We use methods like Gaussian elimination and matrix factorization, which are appropriate for these tasks due to their efficiency with dealing with both real and complex numbers. Solving these equations yields the currents and voltages at various points in the circuit that are critical for understanding both steady state and dynamic responses to these changes. This analysis is critical for designing the circuits that are both efficient and robust, resulting in enhanced performance and reliability. The key informations to this solution for critical circuit problem is the matrix analysis techniques. To solve the system of linear equations resulting from Kirchhoff's law, apply matrix analysis techniques as Gaussian elimination or LU decomposition. This method efficiently handles the complex numbers that result from the impedance of capacitors and indicators in AC circuits. Another point for this circuit problem is Thevenin's and Norton's theorems. By applying these theorems, we can simplify the network analysis. This entails reducing a complex network into a two-terminal circuit, which makes it easier to analyze and comprehend the effect of individual components in the overall circuit behavior. So that was the solution for these problems. In the conclusion, our analysis of traffic flow optimization and electrical circuit behavior shows that the use of linear algebra to solve the complex real-world problems. Linear algebra is combined with linear programming gives an effective framework for modeling and optimizing urban networks and traffics. This approach improves traffic efficiency and reduces congestion by strategically managing traffic lights and the road capacity. Showing the value of mathematical optimization in urban planning, linear algebra is useful for analyzing and solving circuit problems. Matrix analysis techniques enable the precise calculations of currents, voltages, and circuits in a containing variety of elements such as resistors, capacitors, and indicators. Both scenarios highlight the importance of linear algebra in the engineering and planning. These techniques not only deliver solutions but also insights the lead and better decision making for more informed design strategies. The insertion of theoretical mathematics and practical application demonstrates that the linear algebra's transformative potential is addressing and solving a wide range of problems in modern society. Thank you for joining the presentation.